All right, we are live. Everybody see this okay? Okay, so I'm Ben, employee of Columbia. Columbia is basically a subsidiary of the federal government and has received plenty of research grants to develop STAN, also co-founder of STAN Group, which provides a variety of things targeted at businesses wanting to make use of STAN, and according to Columbia University policy, those two things together imply that I have to disclose these things in public presentations. So with that out of the way, what we're talking about today, what we're doing this week. So today we're going to be talking about diagnosing problems with models that are estimated by STAN. That is a very important step. But if you take the time to do it, you should not get caught using a model that's not, doing particularly well. We have homework due before class on Thursday. Talk about the answers to those couple questions. And a number of people have been asking me about the first one. So if it helps, you can think about the first problem. Imagine we were doing Metropolis Hastings and we wanted to set up a function and proposals for theta would come in, and we need to evaluate those proposals to compare them to what value of the log posterior we got previously in order to evaluate the Metropolis Hastings acceptance criteria. Now, we're not actually going to do all that because there's no reason why you should be using Metropolis Hastings. We would do a similar sort of thing in STAN, but we're not ready to learn the STAN language yet. So you can just imagine this function is, taking in proposals for theta and then evaluating the numerator of Bayes' theorem in log units. You can drop constants if you want, but it doesn't really matter if you do or you don't. So there's nothing random about the function. There's no draw from a prior predictive distribution or anything like that. It should be entirely deterministic given the inputs of the argument to that function, which are, if I remember correctly, theta, which is going to be a parameter vector of length 16. There's 4 gammas, 4 pi's, 8 phi's. And then the next two arguments are the data. So in the observations that don't have clues, there's going to be 4 possibilities. And so you need to pass an integer vector of length 4 that says how many cases that you didn't see clues fell in each combination of x and y. Then the next argument is a vector of length 8. Those are for the observations where you do see clues. Count an integer vector of how many times it fell in each of the 8 categories defined by the intersection of x, y, and k. And then there's 2 more arguments to the function, or maybe 4 more. The alphas and the betas that go into the beta prior for the pi's and for the phi's. So you have this beta prior on the pi's, which is the conditional probability of x given the type of the unit of observation, and the phi's, which is the conditional probability of seeing the clue when you seek it. Those both probabilities, it's reasonable to put a beta prior on them, but the beta prior entails 2 inputs: the first shape parameter, the second shape parameter. We've called those alpha and beta. So, if you had any actual insight into this data generating process, you could choose those alphas and betas to be consistent with your beliefs about the prior mode and the prior median for those things. But in this case, you don't. And in this case, you don't even have to actually evaluate the function. You just have to define the function. So whatever those shape parameters are, they do need to be positive. You just plug them into the d beta function and you can evaluate the beta priors for any of those things. Anyway, so we'll talk about that. We'll talk about the other problem on Thursday. And then Thursday, we'll also talk about comparing competing models that have sort of passed your, diagnostic screen. And now you're interested in saying, well, how much better or worse is this model than that model? Okay? Questions? Nope. Okay. So as a sort of way of introduction, I want to circle back to something that those of you who took data mining from me in the fall are probably sick of. But those of you who didn't, you could stand to hear it at least once. There's an approach to quantitative analysis known as supervised learning, which comes less from statistics, more from computer science and engineering. Where, it's the sort of thing that Facebook, we were talking about last week, they're using Stan, is in a lot of the same vein, trying to estimate models where the main output that they're interested in is how well does it predict future data. And the supervisor learning approach almost always goes something like this, maybe with a little bit of variations on it. But first thing, you obtain a set of data, and this is usually going to be a lot of data. And you divide that data. It doesn't have to be exactly equal, but you divide it into what's known as a training data set and a testing data set. Oftentimes, you put like 80% of your observations into the training data set and 20% of your observations into the testing data set, something like that. And then in step 2, you estimate, or what data mining people refer to as train your model, which is to obtain parameter estimates. And again, with all these data mining things, you're going to typically be obtaining point estimates. It's a solution to some optimization problem. And the key thing is, well, this optimization problem is going to consist of one term that captures how well the model or the procedure fits the training data, and another piece to it that penalizes the parameters to the extent that they're not zero. But the key point here is, one, well, what function are you minimizing to obtain parameter estimates? But two, this function is evaluated using data from the training subset only. So you solve this optimization problem, you obtain point estimates of the parameters, and then you take those point estimates of the parameters and evaluate how well the model predicts, or some function of how well the model predicts in the testing set. So let's just imagine we're doing this with like linear regression or something like that. So we divide our data into training set and testing set. We estimate the coefficients of the model using the training data only. So we do like x prime x inverse x prime y using the x and y data from the training set only. That gives us point estimates of the regression coefficients b. And then we use that estimate of b, multiply that by the x in the testing data set, which we held out, and now we get y hats in the testing data set. We can compare those y hats to the actual y's in the testing set. We can get residuals or errors, and then we can calculate some function like mean squared error in the testing set. And that gives us a metric that we can compare different models, different procedures. So we could try a bunch of linear regressions with different combinations of the predictors, or we could do a linear model and some sort of a model that has interaction terms. Variety of different ways we can go with this, and we need, or they think they need, some way of comparing which model predicts best for future data, or if you don't have future data yet, the data you held out to constitute your testing set. And this is a very core idea in supervised learning. There's not a whole lot of dissension from it, but I think if you ponder it a little while, it leaves a lot of things to be desired. So the part of the reason for this is that data mining people correctly pointed out that if you evaluate your model on the same data that you estimate the parameters of the model with, you will tend to overfit the data that you have and not predict future data as well as you could. And so they do sort of two things in response to that. One, they introduce the penalty function that goes along with the misfit function to, that you minimize to obtain the parameters. The penalization thing acts a lot like a prior, where you can sort of inject more personal information that these coefficients tend to be close to zero, and you need a lot of evidence in the data to take them far away from zero. So penalization is one thing, but probably the main thing is this idea of, before you start estimating models or anything like that, you separate your data set into training and testing, and you only use the training to estimate the models, and you only use the testing to evaluate different models. And we'll talk more about model comparison, like I said, on Thursday. But I would say, from a Bayesian perspective, it's not necessarily, obviously the case that the reason why, traditional frequentist methods tended to predict poorly is because you're, using the same data to estimate them as you are to compare different models. What a Bayesian would be more likely to say is, well, the root problem here is you're using optimization to obtain point estimates, and you're not taking into account your uncertainty in those things. So if you use the posterior mean or you use the posterior median rather than the posterior mode, then your propensity to overfit your current data and predict poorly in the future data is going to be dramatically diminished. So from a Bayesian perspective, it's not so much how you separate out the data, it's, are you doing optimization to obtain a point estimate, or are you trying to draw from the entire posterior distribution of the parameters, and then, if you want to, maybe take the posterior mean or the posterior median as your point estimate, but that posterior mean, posterior median is a richer quantity. It takes into account more information in the data because the posterior distribution is a function of the data. And if you do the mean or whatever, you're averaging over the whole posterior distribution as opposed to just focusing on the one point that gives you the maximum posterior density. Another thing is, Bayesians are very skeptical of this idea of using less data than what you have. Because for Bayesians, you're always seeking a posterior distribution, or at least draws from a posterior distribution, whose PDF is the conditional distribution of everything you don't know, which is represented by theta, conditional on everything you do know, which is, y and x and all sorts of things like that. So if you're seeking, really genuinely seeking this posterior distribution, why would you condition on less data than what you actually have available? Why would you only condition on the y and the x in the training data and not use the y and the x in the testing data in order to get a more precise posterior PDF for theta? So I think, data mining people would say, well, we're using this technique in situations where we have so much data that, the uncertainty in the parameters is not really a big issue. We can afford to sacrifice 20% of it toward the goal of, being able to choose which model or which procedure is better, because that's, a really important choice. We'll talk on Thursday that there's Bayesian ways of doing this where you don't have to pay a 20% penalty. But again, I would say, the data mining people often sort of say, well, this thing that I'm doing has a Bayesian justification. But they're never doing what Bayesians would do with it. So, if you're estimating a model with a lot of data, that's fine, but you probably want to estimate a really rich model that takes into account, a lot of the heterogeneity in this data set that you have, that's so large or whatever. As you collect more and more data, you're sort of lumping together more and more slightly different data generating processes. And we'll talk about hierarchical models after spring break that help us disentangle that. But what you often see with this sort of machine learning data mining approach is very simple models being estimated on a lot of data, when it would probably be better if you were estimating a model that was a little bit more complicated than what is typically being done. And even if you have a lot of data, if you're estimating a model whose complexity is comparable to that, you're still going to have a fair amount of uncertainty, at least about some parameters in the model, and you need to be taking that uncertainty into account when evaluating competing models or doing diagnostics and things like that. And so from the Bayesian, the goal is always can I get the best posterior distribution that I can, and to do so you would usually want to condition on all the data that you have, rather than only like 80% of it. So questions about that? So some of the differences there.
So are we going to learn Bayesian machine learning in this context, or this is just like motivation?
This is more motivation. Bayesian machine learning doesn't make a whole lot of sense to me as a phrase. Bayesian learning does. Bayesian learning with a computer does. But what is distinct about Bayesian machine learning that's not Bayesian learning with a computer? I don't really know. I know a lot of people use that phrase. It tends to mean, we're going to do something that's not MCMC. And if you're not doing MCMC, then I seriously question how Bayesian you are, because that's really what gets us draws from the posterior distribution. And if we're not drawing from the posterior distribution, then we're not Bayesian. All right. Okay. But this idea of, well, we're going to compare models, we're going to evaluate models based on how well they predict future or held out data is, reasonably intuitive. But from a Bayesian perspective, what we want is the distribution, or at least draws from the distribution, whose PDF is the conditional PDF for future data given past data. So y tilde is going to be a future data point. That's a random variable in the present. And the vector of data y is the data that we have available now. So, this is just another PDF. And, we want to be able to either analyze this PDF directly, which is usually going to be impossible, or to obtain draws from this PDF, draws from the distribution that has this PDF, which turns out to be pretty easy. So this is just the posterior predictive distribution that we've talked about before, but it's so important for Bayesian analysis that it bears repeating. So imagine, instead of drawing from the distribution of y tilde given y, we drew from the joint distribution whose PDF is y tilde and theta given y. So if we could draw from that bivariate distribution, we'd be just fine. We could, ignore the draws of theta if we really wanted to, and just focus on the draws of y tilde and be able to describe them and make probability statements about them. So yeah, sort of technically we want the first line drawing directly from the distribution who has PDF y tilde given y, but it would work just fine if we could draw from a bivariate distribution of y tilde and theta given y, because either way we'd have our draws from y tilde, which is what we're looking for here. And drawing from the joint distribution of y tilde and theta, conditional on y, is not difficult. So, I didn't put the integral up here, but technically if you wanted to go to the distribution of y tilde given y, all you have to do is integrate the joint distribution of y tilde and theta given y, integrate theta out of it, and now you have a PDF for y tilde given y. That integral is going to be impossible, so don't waste your time doing it. But conceptually, that's all it is, and that's the reason why we can get y tilde from the joint distribution if we're obtaining draws rather than doing the integration. So if we have this joint PDF of y tilde and theta, we can use the general multiplication rule to write that as the product of the distribution for y tilde given theta and y. Actually, y is not particularly relevant because theta contains all the information about that's provided by y. But anyway, we have this conditional distribution of theta of y tilde given theta, and we multiply that by the posterior distribution of theta given y. And those two things on the right-hand side multiplied together give us a joint PDF for y tilde and theta. So again, that would just give us a PDF, which is not particularly useful. What we want is draws from this distribution, and we can obtain that in two steps. So first we need draws from the posterior distribution, whose PDF is f of theta given y. And then we want to take a realization from that distribution, call it y tilde, and use theta tilde. So realization of the posterior distribution is theta tilde. And we want to use theta tilde to then draw from the distribution of future data, whose PDF is f of y tilde given theta tilde. So we just do this same process over and over and over again. Take a draw from the posterior distribution, use that draw from the posterior distribution to draw y tilde from the distribution we assumed for the data. So if we're doing like linear regression, that would be a normal distribution. If we have counts, that could be a Poisson or a negative binomial. Whatever it is, we're typically going to have an algorithm that we can draw from the distribution of y tilde given theta. And that's really all we need. And we don't do this in alternating steps. First, we obtain like 4,000 draws from the posterior distribution using Stan. And then we go back, we take each one of them in turn, and we use them to draw y tilde from some distribution we've assumed for the data, conditional on that realization of theta tilde. And we can do all of this with the posterior underscore predict function in the RStanArm package. So really all you for the most part, at least at this stage, need to do is understand what the posterior predictive distribution is conceptually, and it boils down to the thing we have at the top, or draws from that distribution, draws from the distribution whose PDF is y tilde future data conditional on y past data. And so this is really the essence of prediction from a Bayesian perspective. You get a distribution of predictions for each future y observation. Questions about posterior predictive distribution? And while we're on the subject, just to remember, we can draw from the prior predictive distribution in just the same way. The only difference is rather than plugging in draws from the posterior distribution of theta given y, we'd be plugging in draws from the prior distribution of theta marginally without conditioning on the new data. But the rest of the steps are the same, and you can actually draw from prior distributions using the functions in RStanArm. There's going to be an argument that's by default false, but you can set it to true, called prior underscore PD. So if you call stan LM, stan GLM, there's the option to specify that thing to true, in which case stan will run, but it won't condition on your observed Y, it'll just be drawing from the prior. And then you can take those draws from the prior, plug them into, the predictive distribution, get out what distribution for the data is implied by your prior and your likelihood. So a lot of these things, they're not too hard. They could be a little bit tedious if you had to do them on your own, particularly, at this stage in the semester, or particularly if you're still just learning R. But RStanArm automates them for the models that RStanArm supports, which is quite a variety these days. And we'll be learning more of them after spring break. So questions about posterior predictive distribution?
All this we will do on text regression.
Yeah, that's what RStanArm focuses on. Yeah, but it applies to Bayesian models that are not regression models. It's just you're going to have to do more work to obtain those draws with your own code. Yeah, Imad? Yeah, what you believe the data generating process to be before you actually see the data.
What's the, it's not always, in regression, I've heard that, it's not always appropriate to do prediction, right? Basically because, for example, in the data for countries with GDP and per capita income, so on and so forth, population from that kind of data, you don't really care about prediction because countries are different. It makes sense to predict.
Yeah, well, you may care about prediction. I think in this, what we're going to talk about today, you don't actually have to care about prediction the same way data mining people care about prediction. We're mostly going to be making predictions in order to verify that our model is reasonable. But you may actually care primarily about some coefficient in that model, in which case, okay, now you can analyze the distribution of that coefficient, being optimistic that your model was good, or at least knowing where your model is bad. And so,
Y could be the coefficient.
yeah, all those sorts of things. But if you actually deeply care about predictions and you don't care about any Greek letters, which is, for a lot of businesses, that would be the case. Then, you can do that with Stan and with Bayesian tools as well. Get this posterior predictive distribution and analyze it, make decisions off it. It's perfectly fine. But if you want to know about the posterior distribution instead of the predictive distribution, that's fine. If you want to know both the posterior distribution and the posterior predictive distribution, that's fine too. All of it's, available, but you want to make sure your model is doing, reasonably well before you kind of go all in on the analysis. All right. Okay, so today we're going to go back to this model we talked about last week using the political economy risk data. We're going to estimate it with the stan_lm function in RStanArm. Remember, this outcome variable BRB2 is like the logarithm of the black market premium on the exchange rate, relative to the official rate. I'm just going to do a kind of lazy thing and use all the predictors in the data set except the country name. So this is a cross-sectional data set, so it doesn't really make sense to condition on the country. Also, this was for like 1987 or something like that. So we're going to use the P risk data frame. That's where all the variables are. I was pretty skeptical that we could predict the black market exchange rate premium very well. So I said my best guess for the R squared was like 0.2. And then, so that will run. And then you can draw from the posterior predictive distribution by calling the posterior predict function. However, if you just, pass it the posterior distribution produced by StanLM, it's going to use by default the data that you already provided in the PE risk model. So there's no future data here yet. What we're doing is using the posterior predict to answer the question, okay, if this posterior distribution is sort of faithfully capturing the data generating process, what would the outcome look like And does this outcome that we're drawing using the posterior predict function, is that distribution consistent with the data points that we actually have? So this is, sort of reusing the same data to do diagnostics as we did estimation. But because we're using priors, there's less tendency to overfit. And when you do overfit, you'll be able to recognize it. So we're not going to obsess as much as the data mining people would. This posterior predictive distribution of past data, Gelman and Hill calls Y rep, and they use Y tilde to emphasize future data. So this is really more of a replication or set of replication, 4,000 replications really, of the data generating process that we believed generated the past data, which is just called Y. So this is sort of a replication of Y. Questions about any of this? I think mostly we covered that last week. Yes, in that.
So their prediction, this provides predictable for each layer.
Yes. So this is going to be, I didn't put the dimensions here, but it's going to be 4,000 by 62. So we have 4,000 iterations, draws from the posterior distribution, and 62 data points in the PE risk data frame. And so each column of that represents draws from the distribution we believe generated the data for that country.
The coefficients.
No, this is Y PPD. This is simulations for what we think Y should be. But they use the draws that we obtain from the posterior distribution for theta as part of the two-step process. First, we draw from theta given Y. Now we draw from the data distribution conditional on those draws for theta. And so now we have for each country a prediction of what we think its Y should have been according to this model and this posterior distribution.
So like analogous to, if you have to run an analogy to regression, this would be the task of estimation of fitted parameters.
Yes, the one thing that it's somewhat analogous. The way in which it's different, when you do like OLS regression diagnostics, we talk about Y hat, which is just like X times B. This is X multiplied by a draw from the posterior distribution of coefficients. So that all gets added together, plus a draw added onto that from a normal distribution whose mean is 0 and whose standard deviation is a draw from the posterior distribution of sigma. So it's not a deterministic calculation. Each time you have random draws from the posterior distribution of beta and sigma. So it's the same X, you multiply it by a draw from beta, and then you add onto it for each observation a draw from a normal distribution with mean 0 and standard deviation as your draw from sigma. And then add all that together. That is your prediction, posterior prediction for the outcome, taking into account the error variance, as opposed to the Y hats, which in like frequentist regression exclude the error variance. Moreover, you're doing this once for each of the 4,000 draws that you have from the posterior distribution. So it's also taking into account your uncertainty in the betas and in sigma.
They excluded in one case, but they do the prediction on.
Yeah. So in Gelman and Hill, they do it both ways. The frequentist way, which is just like X times B. And then they also say, well, you could do this in R-stain arm with the posterior predict. And it's, X times a draw of beta plus a draw from a normal distribution using your draw of sigma as the error standard deviation. And so this is a fair way of saying, this is what I believe, Y should be for Argentina, taking into account what I believe about beta and what I believe about sigma. as opposed to just, this is my expectation for Argentina, just, based on B. Okay, so the results from this in 2 digits, you can see the medians and the median absolute deviations here. Like in this model, R squared is a parameter, so you get to update your beliefs about it. I started out saying it had a prior mode of 0.2. It came back with a posterior median of 0.35. So I was perhaps a little bit pessimistic about our ability to predict the black market exchange rate premium, but not horribly so. You can look at the other coefficients. Some of them are going to have considerable uncertainty around them, in part because I just threw it in like a bunch of variables without really thinking about them very much. They tend to be highly correlated, etc. And so a lot of our estimates are pretty imprecise here. Individually. Collectively, we might still get pretty good predictions or not. We'll have to see. All right, so this is just the output. So a lot of this stuff for diagnostics is facilitated by our package called ShinyStan, which was written by Jonah Gabry, who graduated from the QMSS in 2014, I believe, and took this class. And so he wanted to make himself some functions that would help him diagnose the output that he was getting from the posterior distributions. And it sort of metasized itself into a package that's on CRAN now and is used by a lot of people that, does everything that Jonah thought is a good idea, or almost all of it. And it's particularly easy to use if the model was estimated using one of the stan underscore functions in the rstan-arm package. We'll show how to do this in a second. But basically, you just pass the resulting thing to launch ShinyStan, and it'll show a web app. So among the things you're going to see in a second, the posterior distribution of residuals. You can plot the observed Y versus the expected value that comes from the posterior predictive distribution. You can plot the marginal distribution of Y, compare that to the marginal distributions that come from the posterior predictive distribution. You can calculate what Gelman and Hill still refers to as test statistics, which is, we're not doing null hypothesis testing in a Bayesian context, but you can calculate any function of Y and Y rep that you want and see if that function, when evaluated at Y, is sort of consistent with the distribution that you get for that function when you evaluate it at each of the 4,000 draws from the posterior predictive distribution. So ShinyStan is a web app. You kind of browse through it, but all of these plots, and actually more plots, can be generated programmatically and statically and just included in our markdown report or something like that. ShinyStan and BasePlot, which is also done by Jonah Gabry, also give you the ability to investigate the convergence and the efficiency of the Markov chains. Usually for the models with rstan-arm, that's a pretty foregone conclusion that they're going to work well. But as you sort of do this with your own models that you maybe write in the Stan language directly, it's going to be incumbent on you to check to make sure that they've converged. And it doesn't hurt to do so even for models that estimated by rstan-arm. If you found one that didn't converge, I would want to know about it. But you shouldn't just assume it for a fact that everything's going to work well. But almost every time you're going to find that to be the case. For models, when we get into Stan in April that you do yourself, it's not going to be as easy to do all this as it is when you use models from rstan-arm. So you're going to have to work slightly harder. You're going to have to write some more code yourself, but you still want to generate the same diagnostics, the same plots. And so doing this with ShinyStan sort of provides a path, a checklist for the things that you want to go through when evaluating any model, particularly any model that's estimated by Stan. Whether that's RStanArm, whether that's BRMS, or whether that's some other package that makes use of Stan, or whether it's you writing Stan code directly and obtaining the posterior distribution for that model. So let me back out of this, go into RStudio, where I've already estimated that same model. And I'm just going to type in, if I can type correctly. First, let me give you some more zoom here. Launch Shiny Stan. And then you give it the object that came out of Stan LM. And so if you're following along, what that should do is open up a browser or open up a tab in your default web browser. Looks like this. And then you can go on to click diagnose, estimate, explore, or more. So let's start with diagnose. And if you click on the tab that says PP check, that stands for posterior predictive check, we can get started with this. So you may have a little bit of a hard time seeing that, but what we have first is a histogram of the observed data. So this is in dark blue here. This is the actual Y. And next to it, we have 6, or maybe it's 8-ish, 7, 8 histograms based on 8 draws from the posterior predictive distribution. So we make 8 simulated data sets using 8 different thetas that we drew from the posterior distribution, and we call histogram on each of those. And so for a well-fitting model, it should be the case that the histogram of the data looks similar to the histogram for what the data should look like according to the model. And those histograms of the posterior predictive distribution, or the histograms of Y rep, these are given in light gray here. And so you can just kind of eyeball those and see, well, do those look like a very similar histogram to the dark blue, or do they look different? How different from each other do the light gray ones look? That tells you something about the uncertainty in your predictions for this outcome variable. But probably the most striking feature is, well, the actual data has this spike for countries that have very low black market premium. And it looks as if our histograms for Y rep are not coming up with a similar spike out here in the far left tail. So our marginal distribution of the data is represented by a histogram, seems to be a bit at odds with the marginal distribution of our Y reps that we drew from the posterior predictive distribution, which is the histogram implied by our beliefs about theta conditional on the data and our beliefs about the data generating process. So when that happens, you might think more carefully, well, what is it about the real world data generating process that's not being captured by my model and hence is not being reflected in the posterior distribution of the coefficients? So questions about what we're looking at here and, the differences that we're seeing.
Like diagnose, should we use those old tools from our regression class, like with the lowest curve to see if it's linear?
We got plenty of tools here, but those are generally going to be better than the stuff that's baked into R already. So it might be a little bit easier if I click the button for overlaid densities. And so rather than seeing 8 histograms, now we see a density plot. Again, the dark line is the density plot for the actual data, the 62 observations we have on black market exchange rate premium. And the light lines, I think there's more than 8 of them now, looks like around 20. These are conceptually the same density functions, but they're the ones implied by our posterior predictive distribution for Y rep. And so this is what the model believes the marginal distribution of the data should look like. And again, you can compare these two things to see if there's any obvious discrepancies. And there are, because the marginal distribution of the data is bimodal. There's a smaller mode of countries that have a very small exchange rate premium. Again, this is logged, so that's why you see the negative numbers here. You know, if you take a log of like a very small number, it becomes a bigger negative number. And then there's a bigger mode of countries that, you know, have a different, you know, looking exchange rate black market premium. And it looks as if our model is spitting out marginal distributions that are a little bit caught between these two modes, rather than distinguishing between them. But, you know, overall, they seem to be closer to the bigger mode and, you know, not really capturing the small mode at all. But they have too much density, you know, in here overall to be considered consistent with the actual data. All right. So if you take the time to look at these, you really ought to know when your model is not doing good. There's, you know, no excuse to not go through this extra step and start comparing, you know, functions of Y rep to functions of the data, histograms, density plots, whatever. And, you know, knowing where your model is not doing good helps you figure out, well, how might you want to change your model? What data additional might you want to collect that would allow you to capture this bimodality in the marginal distribution? So it looks as if we're not really conditioning on the right things in order to be able to capture a data generating process that seems to have considerable heterogeneity. There's, you know, a smaller number of countries that don't have much of a exchange rate premium, and a bunch of countries that do. You'll notice, or maybe you didn't notice, but, you know, there was no variable in here, as far as I know, that says, like, do you have a floating exchange rate or a fixed exchange rate, which you might want to take into consideration if you're modeling black market premium. Or at least that's what economists tell me. So that might be a clue. Maybe we're missing the exchange rate regime variable. No, we are missing the exchange rate regime variable. That might be important. All right. So everybody understand what we're looking at here. And everybody understands, at least for models estimated by R-stan ARM, there's really no difficulty in getting it to produce this plot here. Okay, so, you know, we can also do something like this. On the vertical axis here, we have the actual Y from the data. On the horizontal axis, we have the expectations of Y rep for each of the 62 observations. So taking the expectation over the posterior predictive distribution. And so ideally, this would be, you know, clustered pretty tightly around, you know, upwardly sloping line. So when Y gets higher, we want Y rep to get higher too, or at least in its expectations. And, you know, there's going to be variability around that line, which is captured by sigma and the number of jobs that you're averaging over. And so, you know, maybe it's not horrible, but there's a bunch of countries down here at the bottom that pretty much all have the same value of y, then it looks like we're just, not really doing a very good job with. And, you could actually look up the names of those countries. And if you did, you might find out that they have floating exchange rates.
Is it the average?
It's kind of messy to put like a whole distribution of y rep in strips here. But yeah, like taking the average does get rid of some of the uncertainty that you really have in your y reps. But what we have here, I think, is adequate to emphasize where we have the problem. It's these countries that have almost no flag market premium.
Is this still log units?
Yes, it's the original y, which is in log units. Other questions? Nigel?
So each point of this scatter plot is equal to one histogram that you see before.
The average of one histogram, yeah, on the y reps. So we have average on the horizontal here.
No, this matters, but do we treat y as a random variable?
Yeah,
Because y is fixed, right?
yeah, y is fixed. Y rep is a function of y through the posterior draws of theta. But yes, this is being drawn from like a normal distribution. So yes, it's draws of a random variable and then averaged in this case. So other questions about that? This is kind of like y versus y hat, except it's not y hat. It's y hat plus error and then averaged. So we can do a more similar sort of thing. Look at posterior predictive distribution of the residuals. Just take each y rep, subtract it from y. Now you get a distribution of residuals. You can assess the assumption that you implicitly made that those are going to be normal. Seems a little dicey in this case. I mean, they kind of look symmetric, but yeah, less than normal, which is the assumption that you made when you chose this likelihood. Again, we have distributions here because we can pretty much take as many draws of y rep as we want. But usually like 8, 10, 20 is sufficient to visualize anything that you want to see about that. And Jonah has helpfully written up some explanations for what all of these things are. And he describes it, posterior predictive checking as a simple idea. If our model is a good fit, then we should be able to use it to generate data that looks a lot like the data we observed. And so all these y reps are really generation of data according to what the model thinks the data should look like. And if the data actually looks like something different, then that's a limitation of the model. But yeah, so there's the integral that I didn't explicitly write down. Jonah's not afraid of integrals. Yes?
So in the scatter plot, why are we not using the median?
We could. We could. It's programmed to do the mean. That's fine. But again, we're not using the median draw. We're using all the draws. We get y reps, we draw those from normal distributions, and then we average.
So one left into the 62 countries.
Yeah, for each of the 62 countries, we have 4,000 draws for that country. We take the average of the 4,000 for each country. And that's the horizontal axis here.
Each of the 8 histograms is based on 4,000 draws.
Yes. So there's, if you take 4,000 draws from the posterior distribution, you can make 4,000 histograms. You don't really need to see all 4,000. You can just see 8 and see if you've got a problem.
And if we, rather than just want to eyeball this, want to come up with more rigorous metric for how similar they are, what metric exists to compare these histograms?
I mean, sigma is, the standard deviation of the errors. That should be, if you, calculated the residuals and then made a combined estimate of the standard deviation, it should be very close to the posterior mean of sigma that you could have gotten before. But, really these graphs are probably a better way of diagnosing problems than just calculating some loss function. I mean, loss functions are good if you want to make a decision, you could go this way, could go that way. But if you're just trying to say, like, is my model good or not? Oftentimes graphs are probably the best tool to start with.
What's that second distribution test?
Oh, I forgot to click on that one, but it's also important. So you can calculate any function you want of y, and you can calculate that same function on y rep. So here we have the function t is the sample mean. And so the sample mean of the actual data is a little greater than -3. And the distribution of the sample means of the y reps looks pretty normal, and it's more or less centered on the sample mean of the data. Now that's a bit deceiving because in a linear model, it's hard to mess these first two up. Like, you would really have to only run it for 3 iterations or something like that to get these two back. So the second one is the standard deviation of the y's compared to this distribution of the standard deviations of the y reps. Some of these other ones, the minimum and the maximum, these are a little bit, they can go either way. So the minimum value of the data is -7. But when we drew from the posterior predictive distribution of y reps, we would often get a minimum value that's -8, -9, maybe up to -12.5. So our model seems to be more extreme on the low edge than what the data were. And maybe there's a reason for that we could discern. On the top end with the maximum, seems like we're doing okay. So the maximum value of the data was 3. There's uncertainty here, but it's more or less cutting through the heart of the histograms of the maximum for the y reps. So you can do this with any statistic you want, but for a regression, which sort of is estimating the conditional mean and the conditional standard deviation, it's rarely going to have trouble with that.
On the horizontal axis is the statistic.
Yes.
Vertical is the frequencies.
Yeah. But the frequencies depends on how many observations that you do. So we'll probably learn more about Shiny Stan later. You can do the diagnostics of some of the convergence things, but like I said, in our Stan arm, those are usually going to go just fine. So I don't want to dwell on that today. While we're here, I can show you the autocorrelation. Like I said, with the NUTS algorithm, these are usually going to get very little correlation very quickly as you go back farther and farther lags. So you can choose different parameters that you want to show here. So like the R squared. And then, it'll change the plots. So at 0 order autocorrelation, this is constrained to be 1. But even 1 lag, the correlation goes to 0.1, and then it's pretty much 0 thereafter. That would not happen with Gibbs sampling or Metropolis Hastings. That's pretty much what NUTS gives you, draws that are not very correlated with each other. And thus you only need a few thousand of them to make good inferences about whatever it is you're trying to infer. So, this is pretty typical for Stan and especially for our Stan arm. If you need the estimates in some sort of a table. You can generate them like this. It can export it to tech. It can do a lot of things. If you want to see one of these plots of the posterior intervals, it can do that. You have some more stuff over here. I really like these trivariate plots. So you can put up like, the coefficient on, GDP, the R squared. Come on. So you can see like the point cloud on that. I usually like to put the value of the log posterior on the Z axis. But sometimes you can see like weird shapes here that maybe Stan would have a difficult time navigating. And then under more, there's a glossary for what all these terms mean that you may want to refer to, and some other stuff, help, etc. So you can play around with Shiny Stan. It's pretty much self-explanatory. And you can do a lot of those diagnostics. Okay, back to this. If you wanted to generate some of these plots programmatically, there's all kinds of ones you could choose from. So these are the ones involving posterior predictive checks. So you can read the help on any of these. Basically, when you call these functions, you just omit the PPC underscore when specifying the plot fun argument to the PP underscore check function. So that'll take a string, and this is perhaps more useful if I just give you an example. So the PP check function, it takes the thing produced by ScanLM. It takes a second argument, plot fun, so you can say DINS overlay, and so that corresponds to PPC DINS overlay. You've just omitted the PPC underscore part. And you get the same plot that we said before, dark blue for the density of the actual data, light blue for the density of, in this case, 10 replications from the posterior predictive distribution. Also, all these functions that produce plots in RStan and RStanArm, those are going to be in the ggplot2 grammar. And so you can add layers onto them, or whatever, to change the position of the legend or the tick marks or the sizes or the color themes, all that stuff that you can do with ggplot2, you can do with the plots made by RStanArm because they are made with ggplot2. So here I'm showing how you can move the legend. It used to be, when we did it before, over on the right. Now it's on the bottom. Some people think that's better. Whatever. So all you have to do is like assign these things to an object, and then you can do ggplot2 stuff with them. All right. And then, all these other plots, they do different things. You can pass any of those to plot fun, and you'll get like a little bit different plot. All you have to do is omit the PPC underscore.
They're all going to operate on Y and Y.
Yes. Yes. Questions? Like I said, there are also functions in the base plot package, which goes hand in hand with RStan, RStanArm, Shiny Stan, etc. All that stuff in Shiny Stan is basically calling a selection of the plots in the base plot package. We just separate them out to keep things organized, or try to. So there's a similarly large number of plots that you can use to evaluate whether the thing is converged, whether it was going efficiently, etc. Like I said, with RStanArm, you should do these, but they're almost always going to come out fine. So here is a plot of the R hat statistics. I think we talked about these briefly before. If all the chains have the same means, again, we're going to run multiple chains, by default 4. It probably wouldn't hurt for you to bump that up to 8, just to be extra sure that things are going well. So we have maybe 4, maybe 8 chains, and we have a sample mean for each margin of the posterior distribution for each chain. And we can compare the difference of those sample means across chains for any margin of theta that we want. The R hat is basically a measure of how much those means differ from one chain to the next, taking into account the variability in the posterior distribution. And if all the chains are going to the same distribution, this R hat statistic should be 1. And in this case, for each of the 12 or whatever margins of theta, they have a dot here indicating the estimated R hat. And they were like 1.003 or something at most. So in this case, there's nothing really to indicate that there's a problem with convergence, and there rarely would be with RCNR. But if they're greater than 1.05, you should be concerned that the chains didn't go to the same place. And if you're doing this with the RCNR model, that probably means there's something wrong with your data. Could be something wrong with the code or the model, but probably it's just you're estimating a model that doesn't correspond to how the data were generated very well.
So so there are different chains that go off,
Mm-hmm.
and then they converge.
They should converge.
And then we get that. This is the result of the posterior predictive function.
No, this is just posterior. So this is just the R hats for theta. So they start off in different places. They should converge to the same distribution. We throw away the warm-up period, and hopefully during the warm-up period, they've converged to the same distribution. We take the mean for each chain, and the R hat is basically just a way of comparing the means across chains. And if there's no difference, then the R hat will be 1. And there's no difference here. And there rarely is when doing a model with RCNR. Question, Sean?
The data that kind of like is there like an RCNR model or something like that?
Well, marginally, they are multimodal, and that's fine. The regression model specifies a conditional relationship between y and x. So if the two modes have like different x values, then they should have different y values. But the question is, are you conditioning on the right x's to recover the model have the same marginal predictive distribution as the marginal distribution of the data? In this case, we didn't. And I would speculate that's because we did not include among our x's whether they have a floating exchange rate regime or a fixed exchange rate regime. So I believe it's the case that the right mode was for countries that have fixed exchange rates, and the ones that had almost no black market premium had floating exchange rates. In which case, why do you really need a black market if it's floating anyway? Final idea for this day today is this idea of calibration, which I think is like an engineering word. But basically, according to the Bayesian interpretation, you say, well, if according to your model, y should fall within some posterior predictive interval, let's say it's a posterior predictive interval based on probability of 0.5, then you make those posterior predictive intervals, and like half the observations that you have in your data set should be falling within those intervals. And 25% should be too low and 25% should be too high. When that happens, we say the model is well calibrated. And there's a function called PPC intervals grouped that allows us to do that. So you give it your actual y, you give it your posterior predictive distribution. For the existing y, you can specify Do you want, intervals with probability 0.5 or 0.75, 0.9, whatever it may be? That's the proportion of observations that you should catch within any of these intervals. And I'm also going to group and make two plots based on the value of the courts variable, which is, whether there's an independent judiciary in that country. And so the first one over here is for countries that don't have an independent judiciary. You can see these 50% intervals in light gray. They tend to capture a bulk of the points. The medians have these sort of bigger circles, and then the actual Ys are the smaller circles. So we seem to do a pretty good job of capturing, a lot of the points here. There's certainly some that fall outside the interval in both directions, but we only claim that, these gray intervals should be capturing 50% of the points. And then 25% should be higher, 25% should be lower. It looks like we have more on the high side than we have on the low side. So that's a little bit disturbing. But what is more disturbing is for the countries that do have an independent judiciary, we're missing more on the low side than we are on the high side. And here, these countries, again, that have essentially no black market premium. So you can sort of see that visually with this graph, or you can just capture it numerically by taking, let's say, the 25% quantile of the PVD, the 0.75 quantile of the PVD, that gives you 0.5 intervals. And you can ask what proportion of the actual Ys are greater than this lower quantile and are greater than the lower quantile and simultaneously lower than the higher quantile. And this, in this case, comes out to 0.645. And that's not good. This number should be 0.5 for a well-fitting model. Not lower, not higher. So in this case, we actually are overfitting the data. We're capturing too many points in a 50% interval than we should. And that is in part because I just lazily used all the variables I had in the data set as predictors without really thinking. But we're simultaneously overfitting for the data set as a whole and doing a terrible job at capturing countries that don't have any black market exchange rate premium. So overall, for the whole data set, we're overfitting, but we're sort of systematically missing countries that have no black market premium, I believe because they have floating exchange rates. So on Thursday, we'll talk more about how we might say, okay, we could eliminate this predictor from a model, we could eliminate that predictor. Maybe we could get a better model that at least didn't overfit, but probably in order to capture, these countries down here, we would have to introduce a variable as to whether the exchange rate is fixed or floating.
Each of these lines is just one of those histogram pins.
Yeah,
And that's
it's like one column of the posterior predictive distribution chopped at its 25% quantile and its 70% quantile to define the endpoints here. All right, so we'll pick it up on Thursday. Make sure you upload your homework before class.